And let's talk about translational equilibrium, which isn't there a movie Equilibrium where like the characters shoot guns in weird ways? I don't know. I can't remember. What we're going to be talking about is an equilibrium. And if we kind of just break down the word equilibrium or equilibrium, really depends on how Eastern European your professor is and how they'll say this. This first word here is like equal, right? So we're looking to set things to be equal to each other. And brium, which is kind of like a balance. So we're looking to kind of balance things in equal ways. And we're going to be doing this with forces and Newton's laws. So we're going to be using our classic F equals ma equations. And when we do this, this is just an application of F equals ma. Nothing here is going to kind of be different than we did before. We're just kind of broadening how we've used this old equation. Because when we used to use it, we used to sum up a number of forces. We would sum a number of forces here, and that would equal to a mass multiplied by an acceleration. We're still going to do that, but when something is in an equilibrium, and we're specifically here talking about a translational equilibrium, so moving like left, right, up, down. What's going to happen here is that the forces in the x direction will be equal to one another. So these x direction forces will be equal and opposite. They'll cancel out. And our y direction forces going up and down, they'll be equal and opposite as well. And if we think about that idea of forces being equal and opposite, what this means is that if we were to add them together with one side being positive, so maybe like going to the right is positive and the left is negative, and maybe up is positive and down is negative, if these forces are equal and opposite, that means if we sum the forces up, if we add them all together, then they're going to add up to 0 in both directions, the x direction and the y direction, okay? So we're just looking at adding forces up in the x direction, adding them up in the y direction, so left, right, and then up, down, and setting them equal to 0. And if this holds true, then our object will either be stationary, it won't move because there's no unbalanced forces there, or whatever motion it had initially, it'll just hold that motion. It won't speed up and it won't slow down, okay? Traditionally, we think about the x direction as being the cosine component and the y direction as being the sine component, but that's not always true depending on how you draw your triangles. So what I really recommend for you, you'll see this in your notes right here, you know, the fx and fy, but what I really recommend doing and what we'll do is use your SOHCAHTOA. You're all experts at trigonometry and using sine, cosine, and tangent. Look at what you've drawn, and we'll draw a lot of stuff here. Set up your SOHCAHTOA, and using that, then break things up into their x and y components so that we can add them all together, okay? So let's just take an example here of what we're talking about with this kind of force equilibrium and how we can, break up our components of vectors, these force vectors, into their x and y components and figure out just what's going on. So in our first little example here, we've got a classic monkey, and for whatever reason, monkeys are often used in physics, examples and problems. And this monkey is hanging from 2 ropes, as shown down here in the picture. The only thing that we know is that the tension in the right rope is 35 newtons. So the tension in this right rope over here is 35 newtons. That's it. That's all we know. What we'd like to figure out is what is the mass of the monkey, and then what is the tension in the left rope. So that's kind of a big ask in this problem, right? Like, we only know the tension, and yet we want to know all this other stuff. How in the world are we going to do this? So let's first, Grandpappy Botzer, thank you so much for all of your knowledge and wisdom. Draw a picture. That is the most important thing you can ever do, ever. So what we'll first do is we're going to draw and label a picture for this monkey. So if we take a look at this monkey here, we know the monkey, the monkey's an object, right? So let's just use an orange for the monkey. Maybe it's an orange orangutan. I don't know. That was a bad pun. But the monkey's got a weight acting on it, right? And we know this weight equals mass times gravity. Now, we don't know what the weight is because we don't know what the mass is, but we know it's there. We know the monkey exists, and we know it has a weight pulling down on it. Like, that just has to be the case. We know that this right rope here has a tension in it. So this tension is pulling up on the monkey, up and to the right, and we know that tension's actually 35 newtons here. And don't forget, this tension's actually equal and opposite. It's technically pulling on the wall in the same amount backwards, okay? But we're really not worried about the wall right now, so we'll only kind of draw this purple line going up, acting as the rope. So that's our tension from the rope on the right. We'll call that TR, tension on the right. We also know that we've got a tension pulling up in the other rope. We don't know what it is, but we'll call it TL. That's tension left, okay? So that's our kind of picture, and we've kind of drawn a little bit of a free body diagram here, if you notice. Our monkey was the dot. It has a weight pulling down on it, and then the tension pulling up and to the right in purple, and the tension up and to the left in pink. That's our free body diagram. Now, what is often helpful is to break up this free body diagram into the component forces, the forces actually going in the X and the Y directions. So what we're going to draw here is not a free body diagram. Our free body diagram is up here. That's our free body diagram. But what we can draw here is something helpful for us to see what's going on. So if here's our monkey, and then we've drawn a black X and Y axis here, and let's just shift this axis down a little bit, make it a little easier to look at. If we draw the monkey again on the center of the axis, we know the monkey has a weight acting directly downward. And as we said, this weight was equal to mg. So notice that that weight is on the y-axis. Because it's on the y-axis, we don't have to do anything to it. It's in a good spot. You want things either on the x-axis or the y-axis. Now, if we take a look at our right tension is pointing like this. And we know this value here is 35 newtons. And if we do a little bit of geometry here, since we know that this upper angle here is 30 degrees, if you actually make kind of a rectangle out of this, maybe you'd recognize from geometry that on the inside here, these are some opposite interior angle magic, whatever geometric term that they use in order to say that these angles are the same. I honestly don't remember what it is. I just know that these angles are the same. But this angle right here from the horizontal is 30 degrees. So we could say that this angle here is 30 degrees. And what this allows us to do here is it allows us to say that, look, this 35 newtons up and to the right, that's not on the X or the Y axis. That's a bad value. Well, I don't want that value. I want X and Y axis values. So what we can do is we can split this up. We can say, hey, look, some amount of this tension acting to the right is on the x-axis. And if we wanted to, we could either draw this arrow here to go up and complete our triangle, but it's the same arrow over here. Notice how on the left it's on the y-axis, so it's going up and down. This is the tension from the right on the y-axis. And since we know that this hypotenuse here is 35 degrees, or 35 newtons, excuse me, with an angle of 30 degrees, we can use SOHCAHTOA to find the X and the Y values. We can do the same idea going to the left. The tension to the left, we don't know what it is, but we do know that to the left, there is some amount of tension acting in the X direction. And we know that there is some amount of this left tension acting in the Y direction. So by breaking up our two forces at an angles, we can see that they're acting in the X and the Y direction. And this is very nice because that is what we can add together. We can add things in the X direction together, and we can add things in the Y direction together, okay? So this is what we have right now with our picture. Kind of looks a little bit like, oh, there's a lot of stuff there, but this was really telling us a lot of great information in order to solve this problem, okay? So if we want to use the equilibrium equations for each axis, the x-axis and the y-axis, let's go ahead and find what these x values are and these y values are, and then try to use our equilibrium equations to do this, okay? And remember, the equilibrium equations are basically just saying that the sum of your forces in the x direction, so things moving left and right, have to add up to 0. And the sum of the forces acting in the y direction have to be equal. They have to add up to 0, okay? So that's all we're doing here. So let's go ahead here, and if we were just to create these equations, what would these equations look like? Well, they'd look like, for the x direction, well, it would be, let's choose a positive and negative here. Let's choose a right to be positive, left to be negative. They would be that the tension from the right in the x direction is positive, minus the tension from the left direction in the x-axis. Those have to add up and become 0. For our y direction, if we say, let's just make up positive and down negative, well, both the tension from the right in the y direction and tension in the left in the y direction are positive. So we could say the tension right y plus tension left y minus the weight, it's acting down, so minus the weight equal 0. So those are our two equations that we can actually set up here. And now it's just a matter of saying, do we know any of these values? Is there anything that we can do here in order to solve for some things? Okay, and this is where your kind of math skills start playing into effect. This was all the physics. That's all the physics right there. If you can draw this little picture and then say, look, I'm just adding things in the x and y directions to kind of add things up, like that is the physics. There's nothing too crazy. But we do have to start doing some math in order to actually solve for some things here. The only things we can actually solve for to begin with are the values on the right side here, because, hey, we know that this tension on the right is 35, so let's work out what the x and y values are. If we use SOHCAHTOA, we can see that the x values will be the tension, which is 35, times the cosine component of 30 degrees. And we pull out our trusty calculadoro at that point, and we say 35 times the cosine of 30. Make sure you're in degrees. And we get a value of 30.31 newtons there. And over here, the y component, the up and down, that's the opposite side, so that's the sine component. So this will be the tension, or 35 newtons, times the sine of 30 degrees. And 35 times the sine of 30, that'll give us a value of 17.5 right there. Okay. So let's see, can we put any of these down into this equation here? Well, we can put the 30.31 newtons right here in for Rx. And what's really nice about this is, since this is equal to 0, the x components, they have to be equal. So when we go down here and we rewrite this equation, we say 30.31 newtons minus the left x amount equals 0. Well, that pretty clearly shows us that the tension on the left side in the x direction has to equal 30.31 newtons as well. So we immediately see that this here is 30.31 newtons. So that's a pretty cool feature right there. Okay. Now, what could we do with that? Well, we still don't actually know what the mass of the monkey is, or what is the actual tension force in the left rope, because that actual tension force is this hypotenuse right here. But we actually can start working our way towards it. If we go back into the monkey picture itself, we know this upper angle here is 45 degrees, and if we play the same kind of opposite, interior, symmetric, blah, blah, blah angles, we know that this angle here is 45 degrees. So what this will allow us to do is, since we have the adjacent side of that 45 degrees, and this is the opposite side and this is the hypotenuse side, Well, with one of the sides and an angle, we can solve for everything else here. We can actually solve for TL, and we can solve for the hypotenuse here. So let's see, how do we want to go about and do this? If we want to solve for TLY, here, let's redraw our triangle. Physics is all about redrawing stuff and making things a little bit easier to look at. So that's TL right there. And then here is the left X direction, which we just, well, that's a bad line. Work with me, computer. Which we just found this to be 30.31. And then this is the left Y component. And we know that this right here, this is 45 degrees. Okay, so let's see. If we want to solve for this here, this was our opposite. This was our hypotenuse. This was our adjacent. If we want to solve for TLY, then, well, we're looking for an opposite. We have an adjacent. That means we're using TOA, tangent. And we can say that the tangent of our angle, 45 degrees, equals the opposite, TLY, over the adjacent, 30.31. So we can just multiply by the denominator. So we'll have 30.31 times the tangent of 45 degrees equals TLY. And if you know anything about your unit circle or tangents, maybe you know that the tangent of 45 degrees actually equals 1. So what we're doing here is we're taking 30.31 times 1, which will just give us 30.31 newtons. So now we know what TLY is. It is 30.31, which is pretty cool. Now, if we go back into our force equilibrium equations, well, do we know everything going up and down for the verticals? Well, we do. If we take a look at this, we know that on the right, the Y component is 17.5, and it was positive because it's going up. So that's 17.5 newtons. On the left, acting up, is the 30.31 we just found, so plus 30.31 newtons. Minus the monkey's weight, so minus the monkey's weight, and this has to equal 0 because it's a equilibrium. So if we just add our numbers together, well, they just kind of equal the monkey's weight, because when we bring that weight to the other side, they have to be equal. So we immediately know that our monkey's weight here is 17.5 plus 30.31, which is 47.81 newtons of weight. And since we're looking for the mass of the monkey, it's important to remember that weight equals mg. So all we need to say here is, look, we're looking for the mass. This weight equals mass times gravity, which is 9.8 meters per second squared here on Earth. So we can just divide the 47.81 by 9.8 on each side. And we find our mass of the monkey as 4.88 kilograms. Okay, so that's our mass of the monkey. That's one part of this problem complete. If we want to solve for the other part of the problem, what is the actual tension in that rope? There's a few ways we can do this. We know both sides of this triangle now. If we go back and look at this triangle here, we know that this TLY is 30.31 as well. So what we could do, knowing that this is a right triangle, since we know both legs of the triangle, we could use a Pythagorean theorem, a squared plus b squared equals c squared. That will work. Or we could go ahead and use either sine or cosine and solve for the hypotenuse. Either one will work. So any of those three methods will actually give you your solution for this problem here. Let's just go ahead and use the Pythagorean theorem because we have it. A squared plus b squared equals c squared. Our a and b are each going to be 30.31. So 30.31 squared equals 918.7. And then since there's two of them, we'll just add that to itself or multiply it by 2 for 1837. So we've got 1837.39, and that equals c squared. And then we just want to take the square root of each side. That'll give us C, which is this hypotenuse here. So let's take the square root of that. And we find that our value for the hypotenuse, or the actual tension in this rope, is 42.86 newtons. So this is part B, the actual tension in the rope that the monkey is hanging on from the left-hand side. Okay, so we quickly find there both values. We see that even though the monkey is hanging from both ropes, because those angles are different, the ropes are taking different amounts of force. The one on the right has 35 newtons. The one on the left is 42.86. We used all of our ideas of a force equilibrium in order to solve that. Okay, so what we just looked at here is this idea of a force equilibrium. Our x components need to add up to 0. Our y components need to add up to 0. And just by kind of drawing our free body diagram, we can work that out. Only thing to be careful about is use your SOHCAHTOA. That's not going away. It's very important. And just carefully take your time through the problem. But that's it. That's all that's going on here. It's just an F equals ma problem, but everything adds up to 0. So that is finished. So adios and take it easy.